Okay, thank you.
Great. Thank you, Cheryl. I think we can get started. Yeah, there are a number of people here and online. Good afternoon. Welcome to the HAO Colloquium today. I'm chairing on behalf of Nick, who got a schedule conflict. So it's my pleasure to introduce our speaker today, Dr. Visha Ray from the Keihan Space. Did I pronounce that correctly?
Yeah, you pronounced it correctly.
Okay, it's actually a local partner. Okay, yeah, Visha is a senior astrodynamics engineer at the Keihan Space, and at the Keihan, Visha is heavily involved in algorithmic development for conjunction assessment, collision avoidance, and orbit determination and prediction. He's also working with the Space Weather Technology Research and Education Center, Space Weather TREC, at the CU Boulder in extracting neutral densities using tracking data from commercial satellites. He completed his PhD in aerospace engineering and sciences from CUB, funded by the NASA FATNIS grant, a very competitive grant for graduate students. His dissertation focused on developing improved atmospheric drag models that track the variation of the drag coefficient in orbit. Today he's going to talk about space domain awareness in a enhanced drag environment. Just to point out, we have quite a few friends from NOAA. I know they're interested in that. And also, I forgot to mention Mike. Mike is also sent it from the geospace section, and he's connecting remotely.
Oh, nice.
Yeah. So now it's your time.
Great. Thanks for the introduction now. Yeah, I recognize a few faces, like talked with Tuve a lot, and Zach is actually my colleague at CU Boulder in the Trek Center, and he's moving to different space soon, so he's moving to commercial industry soon. The topic is a little different from what I had said in the seminar. It's still going to touch on atmospheric drag, but I'm going to focus more on the operation side of it, how we do conjunction assessment, and how drag can affect our end products of orbit determination and prediction. So given all the research background that we have here, this might be different, but in a more interesting way. I hope you all can learn something from it. And I'm really excited to be here because my research was an atmospheric drag, so it's great to be here for the first time. Sorry, standard business slide for people working in the commercial industry. I'll just move on from this. Keihan Space is a small company. We are really just 25 people and was founded in 2020. And we are based out of Broomfield. Just drop in anytime. We'd love to have you guys there. Our main products are, we are essentially a software service company, and our customers are satellite operators who own their own assets. So we don't own any assets. We do conjunction assessment and collision avoidance for them. Some of the products that we have are rapid launch conjunction assessment, launch and early orbit phase support, orbit determination, and collision avoidance and conjunction assessment. So let's go through the data that we have right now. Let's look at the number of objects that are out there and really try to understand the scope of the problem we are dealing with when we are doing collision avoidance and CA support. So since 1957, we have launched essentially 6,500 rockets that have placed around 16,000 satellites into orbit. And out of them, around 10,000 objects are still in orbit with 78% in operation. The rest of them are debris, so you cannot really contact them. You can track them, but you cannot do maneuver detection or maneuver avoidance. You cannot actually maneuver the satellites to collision avoidance. And the number of objects that are being launched into orbit, they are rapidly increasing. I'll show a graph where you have essentially the number of objects are steadily increasing until 2020, and there's a sudden exponential increase starting from 2020, and that's mainly because of the decrease in launch cost and the ease in launching many satellites in one go. So right now, the number of objects that we track in orbit are greater than 10 centimeters. Then there are essentially 36,000 objects that we are tracking right now. But that is not an exclusive set. It's not just it's not the total number of objects that are out there in orbit that can pose threats to operational assets. So between 1 and 10 centimeters, there are around a million objects, and less than that, there are 130 million objects. And these objects cannot be tracked, but they can still cause issues with satellites if they collide. For example, if they collide with the solar panels, they can either break them up or they can decrease the operational power that you get from the solar power. So the catalog will begin to rapidly increase as we get more technologically advanced. So Space Fence, which is going to be a new tracking, it's going to be a new tracking technology by the US military, and will track debris smaller than 10 centimeters. So around 33,000 payloads and debris are regularly tracked by the space surveillance networks, and space surveillance networks is essentially operated by the US Air Force. And 2/3 of all tracked objects are debris, and most of them are really in LEO. So LEO is a regime of very, very high interest. And that's where like this room is essentially very well versed with atmospheric drag, and LEO is the most difficult region to work with just because of the sheer number of objects and the dynamical uncertainties in tracking and predicting these objects for satellite operators. So if you look at this graph, the purple region is essentially LEO and the other ones are other orbits. And most of the objects in LEO are debris. So everything that is non-functional and that can be tracked but cannot be operated. And if you look at the number of objects that have been launched in the past, since we started launching satellites, there's a rapid increase in growth since 2019, 2020-ish, and it's just going to keep growing in the next decade. If you look at the planned and launched constellations, some of these constellations people are very familiar with, like Starlink, OneWeb, Amazon Kuiper, Astra. Some of these are already launched, and there are operational as well as non-functional satellites out there from some of these constellations. And in the next 10 years, these objects are going to rapidly increase. Like it's just going to keep increasing. It's not going to stop. And it's not just the US that is launching mega constellations, there's China as well. And I'm sure other countries will follow suit soon. So the scope of the whole tracking problem as well as conjunction assessment problem is just growing exponentially as we are going into the next decade. Similar graph. So to keep up with this growing problem, we need a lot of advancements in many different services as well as technical algorithms. Some of these are ISO tracking, being able to track that many objects, maintaining custody of these tracked objects. We'll talk about some solar storm and geomagnetic storm effects where you can lose custody of multiple objects that are in the catalog. And it's not as easy to get these objects back in a short span of time. And losing track of any objects in the catalog at any point of time can be very dangerous because essentially it's a blackout period for conjunction assessment and collision avoidance. Then algorithms in conjunction assessment and coordination between different operators. So if two operators have two satellites and they know that they are in a path of conjunction with a high probability of collision, who moves the object? Who is responsible for moving? There are no rules right now. There are no rules of the road. So operator communication coordination is a big part of it. Autonomous mitigation, end-of-life requirements. So if a satellite stops functioning or you're at the end of life in terms of the fuel available, do you keep the satellite in orbit or do you deorbit it? And what point do you deorbit it? Debris removal strategies, because they are not just non-functional satellites out there. There are objects created through breakup events or collisions, and those objects are a pretty large chunk of what's out there. But debris removal strategies are being worked on by the government and commercial companies, but the technology is still advancing. We are not at a stage where we can actually remove a lot of debris out from the orbits. Quick cataloging of objects post-launch. So when you launch objects, for example, SpaceX launches hundreds of objects in their rideshare missions, and these objects are being cataloged by the US Air Force. But that cataloging period from launch to being actually cataloged can be from a few weeks to a few months. And in that period, you essentially don't know which object is whose. unless the operator actually has a GNSS receiver and they are tracking their own satellites. And then automated orbit termination. So in order to track these satellites and do orbit propagation and predict where the satellite is going to be, if you start doing it manually for each asset, it's just an unscaled, like it's a huge problem. You cannot really do it for the number of objects that's out there. So an orbit determination process that's automated and can react to changes in your space environment. So if there is a geomagnetic storm and your orbit determination solution essentially starts diverging, how do you automate that? So let's look at a little more detail on the tracking and catalog maintenance process. So the sensors that are out there that are used primarily to track all these objects is the Space Surveillance Network. And it's a worldwide network of ground and space-based sensors, and again maintained by the US Air Force. And it was initially the primary mission of this was to do missile defense. It was not used to track satellites or debris and anything out in space. But things changed once in 2009 when there was a collision between the Iridium and Cosmos satellite. And that essentially posed risks to the military assets, and they started maintaining a catalog of all objects out there so that they can do conjunction assessment to prevent risks to their own assets. And that's being used by everybody right now. So utilizing the SSN, the Space Surveillance Network, to maintain and track the ISO catalog. And today the SSN catalog is more than 30,000 objects with greater than 10 centimeter size. And with the new Space Sense, it's going to increase to 100,000 objects, which are larger than 3 centimeters in size, which is a great thing. We are able to track more objects, which can pose risks to our operational assets. But at the same time, the scale of the problem is essentially increasing almost by an order of magnitude. And STA operations are essentially done by 2 organizations within the US Air Force. It's distributed between the 18th STS and the 19th STS. And the 18th does the surveillance and lifecycle support. So they are the ones who are maintaining the catalog. So when you are looking at TLEs or state vectors of different satellites, that's being done by the 18th, and 19th does the conjunction assessment and collision avoidance support, the launch conjunction assessment support. So the Space Surveillance Network is still the largest catalog of all the objects in space, but there are some other tracking systems out there. One is the EU Space Surveillance and Tracking System, EUSST. Then there are some commercial tracking systems that maintain their own catalogs, like Lockheed, Leolabs, ASKY. And the data is distributed between radar and optical data primarily. And some of these are collaborators with KHAN as well. So when you launch new objects, or there's a breakup event, like newly generated objects, in the sense there's a collision or an object breaks up into different pieces, a fragmentation event. For example, last year, there was a pretty big fragmentation event in geo altitudes where the Intelsat satellite broke up into around 500 objects of debris. So when you have something like that, how do you start tracking these? So you need technical algorithms like to start associating the different tracks that you're observing with the object that you're looking at. So you can use different Kalman filters or MST filters or particle filters to do these. And then after that, you have to do the data association of these different tracks with what you're seeing. So that falls into initial orbit determination. So initial orbit determination is different from orbit determination, where you don't exactly know what the object is, but you're getting data from multiple objects essentially in like one huge measurement file. So you have to take these measurements and associate these measurements with an object. And it's a very difficult problem to do, especially right after a collision or fragmentation event where all these objects are very close to each other. Once you have detected and identified objects, the next thing is to do a catalog maintenance. So building precise orbits. So you do orbit determination of these objects, and that's where modeling of the dynamics and getting good measurements comes into picture. That's where atmospheric drag comes into picture, especially for low Earth orbits. So what are the implications for people in astrodynamics and orbit determination engineers? So when you have observations on certain assets, the first thing is what is the quality of observations? Whether you're getting sparse observations, which are noisy, or whether you're getting dense observations, which are pretty highly accurate. Along with that, what we need to do is have a pretty good dynamical model of the satellite itself. So that basically ties into high accuracy. So if you do orbit determination and you predict your satellite orbit into the future, and your dynamical model is bad, you're going to have a really poor solution. So you won't know where the satellite is going to be 3 days from now. So that essentially involves different modeling of different forces acting on the satellite. So the gravitational model, an accurate atmospheric drag model, and there are multiple state-of-the-art models that are being used by commercial operators. HASTEM is something that is used by the US Air Force and it's calibrated in real time. The models that are used by other operators or even researchers, they are not calibrated in real time. And that's something actually NOAA is working on right now with RAMIPE, and Zubei knows very well. The other forces are accurate representation of SRP, third body perturbations, tides, etc. So these are all forces that act on the satellite, and depending on your accuracy requirements, you will include more and more of these forces. And as you go down the list, they also become more computational intensive, like tides are pretty computational intensive. And the last one is accurate representation of maneuvers. So if your satellite is maneuvering, you need to be able to model that maneuver really well. And depending on the size of the maneuver, your orbit determination prediction errors can be pretty large. But there are cases when you just don't know if the satellite is maneuvering or not. For example, for data providers or SSA companies like us, our customers provide us maneuver files and we can model them very accurately. But anybody else, any other satellites that we track for conjunction assessment, we don't know whether the satellite is maneuvering or not. So that becomes a very difficult problem. The second one is realistic representation of uncertainty, which entails to high precision. So you might have a really good state in terms of position and velocity of the satellite because you have great observations, you have a great dynamical model. But if your uncertainty on the state is really large, because these are all probabilistic, these are not deterministic states that you are estimating. If your uncertainty is very high, you essentially have a ill-posed problem. Your conjunction assessment is going to be really bad because you just don't know where the satellite is, even though your estimate was actually good. So to get more precise states, you have to account for unmodeled dynamics. If I tie that to atmospheric drag, in periods of very high drag, like geomagnetic storms or solar storms, your atmospheric drag model can be like slightly or actually pretty inaccurate from the actual state of the thermosphere. So in those cases, if you don't have a good estimate of your atmospheric density, you can compensate for it by using stochastic, by introducing noise into the process so that your system can, your precision is decreasing, but your system can react to changes in the dynamics much better. And then use of nonlinear filters. Right now, in operations, we tend to use classical Kalman filters or extended Kalman filters to do the propagation. But we know in the community that they suffer from poor representation of the covariances. So the covariance becomes non-Gaussian as you propagate it for longer days. So using slightly more computationally intensive filters like unscented Kalman filter can help with the problem. The next topic is orbit determination prediction, and this is where really the role of atmospheric drag becomes very important. Because when we are doing orbit determination prediction, we need to model our dynamics very well, as we talked about. So right now, KHAN is providing orbit determination prediction services for objects in the low altitude LEO, 500-ish kilometers, medium altitude LEO, and geostationary altitudes. And these are three different regimes with completely different atmospheric drag profiles. So in low LEO, you have high drag. In medium LEO, you have kind of negligible drag. It's still there, but it's a much smaller force and either equivalent or lower than solar radiation pressure. And geostationary altitudes, of course, have no drag because there's no atmosphere there. So if you look at what orbit determination prediction accuracy really depends on, first of all, like we are looking at the data, how we are tracking the objects. So what's the data being used? Is it GNSS data, which usually is it provides you a lot of information on the object because you're getting estimates of your state, position, and velocity, and then you're using that to get better orbit estimates. Or you can have optical or radar data, which are providing you 2D information. So that's the right ascension and declination, basically looking at an image in the sky and getting an orbit out of that, or radar, which is tracking the radial and the radial rate information of the satellite. Or it can be a combination of all of them. So you're combining GNSS data with optical radar data, which is great. Then you have more information. If you look at these two plots, the first one looks at the GNSS measurement residuals of a very well-constrained OD, orbit determination in low LEO. So if you look at the residuals, which is basically measurement minus what you're predicting, they are, first of all, zero mean, as they should be. That's the sign of a good OD solution. And there is a lot of data, and it's not diverging at any point. If you look at the second solution, it's the residuals between a radar measurement and your orbit prediction. So in this case, if you look at the first plot, so that is just the prediction minus the measurement without any filter updates. And you can see, first of all, the first thing that you notice is that the graph is very empty, like there's barely any data. And there are a few points here and then scattered here and there over multiple hours. So that automatically provides less constraints to the problem and becomes more difficult to deal with. And when you have poor dynamics, you just don't know your CD, you don't know what the mass is. In some cases, you actually don't know what the mass and area, cross-sectional area is. Combining all these factors, it becomes very difficult to do an orbit determination in an object like this. And in this case, if you look at the last, it's a bit hard to see because it's so sparse. But the last data arc, you have pretty huge residuals. They are 10 to the power 4 scale residuals. That just means that in this case, there is data which is cross-tagged, which essentially means that the sensor is looking at multiple objects in the same area and just doesn't know which one is which. So it is giving us the entire data set. And we are supposed to be rejecting the cross-tag data automatically through our orbit determination system. So depending on the data, the OD problem can be very difficult. The second is availability of accurate maneuver information. So in the first case, if you see the dashed lines represent the maneuvers, and the graph looks very similar to the ones that we saw in the first, in the last slide. Like the residuals look good, they're zero mean, and everything looks pretty converged. In the second case, you can see a clear divergence. It's not zero mean anymore. It's the solution is diverging after a large maneuver. So depending on how well you know your maneuver, your OD solution will vary. And the third one is availability of spacecraft parameters. We need spacecraft parameters, mass, cross-sectional area, etc., to be able to model our dynamics well, which is atmospheric drag and solar radiation pressure. If you are in a region with very high atmospheric drag, let's say very low altitudes, 300 to 500 kilometers, and you don't know what the cross-sectional area is, the first few days of your OD solution is going to be pretty bad because you're starting with essentially no information. And after that, as you estimate the CD better and better, your OD solution is going to converge. So if you have a case when you have cross-tag data, lack of maneuver information, and lack of spacecraft parameters, they're all happening at the same time, what do you do? Like there's essentially nothing you can do other than waiting. You wait for many days of data to accumulate and get a better and better estimate on your state and your spacecraft parameters. So atmospheric drag effects can trickle into multiple areas of um, tracking operations. The first one is LEOP, which is launch and early orbit phase. So when you have newly launched LEO objects that rely on propagation of post-deployment states to make contact. So when new objects are launched from a rideshare mission, for example, your GNSS receivers are not turned on immediately, right? You don't have any state other than what your launch provider is providing you. So they tell you that this is the position and velocity of your satellite right after launch, but that's something that's estimated. So these states are then propagated forward, and then the operators predict that the satellite is going to make contact with your ground station at this certain time. Now, if you have a launch at during a period of really high storm conditions, when your atmosphere is inflated and you have a highly dense atmosphere, your propagation is going to be bad. It relies on your atmospheric drag models, and atmospheric drag models suffer from larger errors during storm conditions. So what do you do in those cases? So in such cases, when you have larger propagation errors right after deployment, it will delay contact with the operators, which will freak them out. And it'll also delay cataloging. So the 18th, which is cataloging these objects after launch, it can take them many weeks to be able to catalog these objects. And that delays your conjunction assessment and collision avoidance process. Then you have object deployments. If an object is already in orbit and is well cataloged, but it is releasing something from it. For example, there are satellites that have some sort of a material holding the solar panels together. When they release that material, you have to be able to track both these objects, and it suffers from the same issues as LEOP does. It's just a smaller scale problem. You have two objects to track in that case. Then atmospheric drag effects have issues, of course, in orbit determination tracking. If you have an object which is well cataloged and we are doing OD on it for many days, and you have a very good estimate of your CD, and you have a sudden change in your atmospheric drag due to a large storm, for example, what happened during May last year, your CD will suddenly change, and your automated OD will usually fail. And in those cases, the OD analyst has to go and tune a bunch of parameters, inflate the CD covariance so that the CD reacts to the change in your atmosphere. This thing can be done for a few objects. A human can go and actually change these things to react to a solar storm, or react to space weather storm conditions. But what happens when you have many, many objects? The larger the number of objects, the greater is the cost of manual human intervention. Then the other thing is combined effects. When space weather effects coincide with periods of sparse or noisy tracking data and inaccurate information on your spacecraft, that times doing an OD and getting a proper OD solution becomes extremely difficult. And we have seen that for a few objects in our operations as well. And a reminder that commercial operators do not have access to a calibrated model. We rely on modeled atmospheric densities, and they are not always accurate when you have a space weather storm. The next thing is the precision of your orbit determination solution. We talked about covariances. Orbit determination suffers from this big problem that if you are estimating your state and you are not paying attention to the covariance of the state, it's possible that your covariance can decrease to a very small number. And the problem with that is that it's not realistic. Your actual error in your satellite states is larger than what you're expecting it to be. Your covariances are too small. And that can cause pretty bad estimates of your probability of collision if your covariance is unrealistic. So in these cases, you have to make sure that your covariances actually reflect the actual error in your prediction. And that ties into the process of covariance realism. where you are tuning the noise in your process based on what the error is. And objects in low Earth orbit suffer from this problem a lot, and the main culprit is atmospheric drag, because atmospheric drag introduces errors in your propagation that increases the errors in your predicted states, but the covariance does not reflect that unless you tie in the process noise with the errors in your atmospheric drag model.
Sorry for interrupting.
Yeah.
Quick question, what is PC calculation?
Oh, sorry. PC is the probability of collision.
What's that again?
The probability of collision. So what is the probability with which your objects are going to?
Oh, sorry.
Like-
Our last slide is,
Yeah.
I'm not too familiar with the acronyms. But
Oh, sorry. I should have, yeah.
if you don't mind, just.
Yeah. So these basically are covariances are used for conjunction assessment and probability of collision calculations. So CA means conjunction assessment, where we are predicting our orbits into the future and looking at what the possibility of conjunction is. So when two objects come together, like come pretty close to each other, and the metric of that conjunction assessment, or CA, is the probability of collision. Like, what is the probability that these objects are actually going to collide, and what is the missed distance between them? So these are the two main metrics we use: the probability of collision and the missed distance.
What would be like typical minimum distance that you would raise a warning?
So our main metric is PC. So if something decreases less than 1e minus 5, the probability of collision is less than 1e minus 5, sorry, greater than 1e minus 5, we will ring the alarm bells that, hey, this is a high probability of collision alert. And if something is greater than 1e minus 3, that's an actionable item. That means you definitely have to maneuver because the probability of collision is too high. Missed distances can vary from hundreds of meters to a few kilometers.
Okay. I suppose that also depends on the size of the.
Yeah, it depends on the size of the object for sure. And that's basically the hard body radius. So it's not just the size of the single object, it's a combined size of the primary object and the object with which it is going to have a conjunction. So we basically draw a sphere around those two objects and call it the hard body radius. That's the size of interest. Yeah, please stop me if I do not explain acronyms or something that you're not aware of, because this is a slightly different topic than what you guys work on. Hope you can get something from it.
Good to learn.
So the way we use space weather information, as I talked about, atmospheric drag plays a pretty big role in the work we do because of orbit determination and dynamical modeling. So we use space weather files for that. The main things that we use are the solar indices and the AP indices, which are used by the atmospheric drag models. It's possible that we have seen outages in the space weather files that we ingest for operations. And it's possible that there might be cases where you have a solar or you have a space weather storm and the data outages happen at the same time. So you don't get space weather files and you have a space weather storm at the same time. And then conjunction analysis requires uncertainty propagation, like the covariance propagation. So the calculation of probability of collision and missed distance, it requires essentially your covariances to be propagated in a realistic manner. So we need to incorporate uncertainties due to density and CD, and we don't have a lot of information on what the actual error in your atmospheric model is. What we use is the density, atmospheric density itself in the process, but we don't have any estimates of what the uncertainties on the density is, which causes unrealistic orbit uncertainties. Then orbit determination. What level of process noise should we include in your CD estimate? That again ties to what is the error in your atmospheric drag model. If you have a small error, you would want to introduce low noise in your CD. If you have a large error, you would want to inflate the noise in your CD. But these things are really done by operators in a very trial and error manner. We look at past data, we look at orbit overlaps, and then we go and change these estimates moving forward. But if we had uncertainties from the atmospheric model, this would make life of operators easier. And if there, yeah, go ahead. Yeah.
The CD, I guess, is atmospheric drag coefficient.
Yeah, CD is the atmospheric drag coefficient. Yeah, it's so CD is really the scale factor that we use to scale up the atmospheric drag model, because atmospheric drag suffers from errors because of the density. So we estimate a scale factor to the atmospheric drag force when we are doing orbit determination, and that we term as CD.
Is that mainly determined by the morphology and the size of the object itself?
Yes, so you can get a prediction of your CD by looking at the size, the cross-sectional area, and the material of the satellite.
Yeah.
But more often than not, the CD that you predict is not going to be the CD that you observe, just because your density is different. There are issues in your measurements, there are issues in other dynamics. So CD becomes this scale factor that absorbs effects from everything. It could absorb effects from other unmodeled forces, which has nothing to do with atmospheric drag, but it's just acting in the same direction.
What about the altitude? Does it, is there altitude region where CD has more variability, expect more variability?
Yeah.
Altitude?
Yeah. It doesn't depend as much, the variability doesn't depend as much on the altitude. CD is definitely, so the satellite orbits are much less sensitive as you go higher in altitude to CD. So you can see more variability there just because it's not as sensitive. Like CD does not have a bigger role in the orbit effects. So from day to day, as you're doing orbit determination, you can see the CD jump up and down a lot, but it's really not affecting your orbit as much. So the jumping up and down is not really causing any issues.
Mm-hmm.
If you're at a very low orbit where the orbit is very sensitive to CD, any small jumps in your CD can have a really huge effect on your orbit prediction. So you usually see that the CD is going to be much well constrained. So higher variability in higher altitudes, but also the effects are smaller.
But
Yeah.
what you're saying is the CD is not that physical anymore.
It's not physical. Yeah, exactly. It's not. You can see extremely unrealistic values of CD as you go higher up in altitude. It could be intense. It could be negative too. We have seen negative CDs crop up. Yeah.
So again, just follow up on that. At the high altitudes, CD may be more sensitive in terms of like the drag effect they can get. So does that mean you can get a more accurate estimation of the CD just using the data for a high altitude? Because that seems to be where they will stand out the most.
CD and higher altitudes?
Ideally, yeah.
No, because the orbits are lower, have lower sensitivity to CD. So CD can jump around a lot when you're at higher altitudes, but you're estimating CD based on the effects of atmospheric drag on the orbit, right? Since the CD is causing the orbit to change, CD/atmospheric drag is causing the orbit to change by a very negligible amount as you go higher up in altitude, you just don't get a good estimate of CD. Okay. But it also it does not really affect our operations as much because the sensitivity is so small. It could be 10, it could be negative, but we don't really care because atmospheric drag has such a small role to play in higher altitude, just in terms of operation.
Okay.
Yeah.
That's good to know.
So for orbit determination, again, how much prediction accuracy can be expected given the space weather and density model? These are usually harder to predict, but for asset to asset, if you have a history of information of previous errors, you can make empirical models out of it. But it would be very useful for operators if atmospheric drag models or atmospheric density models actually came with uncertainty information. And then we have long-term forecasts of space weather for reentry analysis. For right now, if we do lifetime studies or mission planning for satellites, we tend to use empirical models of F10.7 of how the long-term F10.7 is going to look like. But for AP and geomagnetic storm, we don't have anything. So the uncertainties on your lifetime can be, the uncertainty on envelopes on your lifetime can be pretty large. Then the next topic is conjunction assessment. How do we actually do conjunction assessment? That really ties in all the everything that we have talked about before on atmospheric drag, dynamical uncertainties. But how do we really do CA or conjunction assessment? How do we find out what the probability of collision is, what the missed distance is going to be? Wally got conjunction assessment very well. So this is a video from one of my favorite movies, Wally. So conjunction assessment is being done by the 18th and 19th. And it can be essentially divided into 4 main tasks. The first thing is collect satellite data, figure out where your satellite is, then do orbit determination and prediction. SP propagation means special perturbations propagation. Special perturbations propagation catalog is the catalog that the 18th maintains. Special perturbations or high accuracy catalog, which is HAC. Sorry for all the acronyms. I used to hate seeing acronyms in slides, and I'm doing the same thing now. But yeah, HAC is the high accuracy catalog. It's the catalog that I was talking about earlier. So what the 18th has to do is once it does the orbit determination, once it maintains the catalog, take that catalog and screen it. And by screening, I mean take every object in the catalog and propagate it forward, and then look at a propagation of a different object in the catalog and see if they're going to intersect. An intersection between 2 orbits means conjunction or collision. So that's what the screening process is. Like take every object in the catalog and screen it against every other object in the catalog. And once you have screened it, once you get results, and then you rate them according to what the probability of collision is. The highest probability of collision with the smallest missed distances are going to be at the top, and then you have lower and lower probability of collisions. If you have something which is high probability of collision, something in the range of 1e minus 5 or greater, you send alerts to the appropriate operator. So if some satellite has a very high probability of collision with another object, the 18th is going to send these alerts called conjunction data messages to both of these operators. And conjunction data messages are essentially contain your state at the time of conjunction, your covariances, and what the probability of collision is. Now, let's try to understand the scale of this problem. We have already talked about the number of objects that's out there in space, and we know that it's increasing more and more as we are launching more objects. Plus, there are multiple fragmentation events that are happening. This slide is a bit outdated because minor fragmentation events happened in 2023, but there was a very large fragmentation event that happened last year, which was in the geo altitude, the Intelsat breakup, which caused generation of 500 new debris objects. And objects are being added all the time. They're also decaying, at least in LEO, they are decaying all the time too. But usually from year to year, we see a net increase in the catalog, never a decrease, just because the sheer number of objects we tend to add every year. If you look at the number of conjunctions that you receive in LEO over a 3-day period, it's around 2,500. And at the altitude of interest is around 600, 700 kilometers. And that's a pretty large number of conjunctions to deal with in the LEO regime. Now, if you look at the numbers, just how many objects that we have to screen against, a catalog to catalog screening is, so we have 36,000 objects. And if we start doing a conjunction assessment or screen every object against each, like one object has to be screened against all the other objects, the number of conjunctions that you'll be investigating is 1.25 billion, which is essentially a problem that we cannot deal with because it's extremely computationally intensive. But at the same time, you will not be screening every object against every object because these are in completely different orbital regimes. It wouldn't make any sense to do a conjunction assessment for an object in LEO with an object in geosynchronous orbit because they're completely different altitude. They will never have a conjunction. So in the 80s, Hoots et al. They devised a set of filters to essentially bring down the number of conjunctions that our processes or that our processes have to deal with. And some of these are very intuitive, very where you can look at the satellite orbital elements, which is the apogee and perigee, like the lowest point in the orbit with the highest point in the other orbit, and see how far apart they are. If they are above a certain threshold, there will never be a conjunction between them. So you can reject all those conjunctions. And similarly, there are other filters like orbit path and time pre-filter, like at what time the conjunction is going to be. And then there have been further more developments to reduce the number of conjunctions even further. I'm not going to go into the details of these, but some of these look at, instead of looking at just the orbital elements, which is like a coarse rejection of conjunctions, there are some finer rejections of conjunctions by looking at the states themselves, like looking at the XYZ components of the different objects. And if they are above a certain threshold, if the differences are above a certain threshold, reject them. So if you look at all these filters and apply all these filters to all the objects that are being tracked right now, it goes from 1 billion to around 600,000 CDMs per day, which is still a huge number to be sent out to people, to different operators, or to deal with, but it's at least not 1 billion. And one of the first probability of collision studies that was done, like what is the probability of collision of an object colliding with another object? It was done by Kessler et al. Of the Kessler syndrome fame. They developed equations for debris flux, and if a satellite is passing through a field of debris, what is the probability of collision with that field of debris? Again, I'll not go into the details of this, but I do want to talk more about how we actually do a conjunction. So when we look at a conjunction between two different objects, we have the states of the object that we talked about, which we do orbit determination on and estimate the states. And then we also get the covariance. And the covariance is essentially an ellipsoid in the XYZ frame. And you can see that it's not a sphere. Like it doesn't have equal uncertainties in all the directions. It's usually elongated in one direction along one axis. And that elongation essentially means, for example, in this case where the arrows are, that elongation means you have higher uncertainty in that direction. And there are a few reasons why the uncertainties can be higher in one direction, but the main thing that would come to our minds is atmospheric drag again. In LEO, when you have a large error in your dynamics because of atmospheric drag and you propagate it forward, you're introducing larger uncertainty in that direction. And atmospheric drag acts in the in-track direction, which is the direction of travel for the satellite. So that's where you have the highest uncertainty for the object. So in LEO, your covariances are going to be always and always elongated in the in-track direction because of atmospheric drag. And there are a few ways where you can actually do conjunction assessment. And one of them is doing a 3D covariance ellipsoid. So calculating how these 3D covariance ellipsoids are going to interact with each other. But it's a very computationally intensive process and essentially cannot be done for the sheer number of objects that we have cataloged right now. So what we do is we do a 2D simplification of that. So we project the covariance onto the B plane, which is like the plane of encounter of these two objects. And the requirements for this 2D simplification is these things. The main thing here that I want to focus on is the high relative velocity. So for this method to work, for the simplification to work, the objects need to come at each other with a high relative velocity, which essentially means two objects in a head-on collision. So your velocities are directed towards each other. So you have a very high relative velocity there. But then you have encounters where the velocity can be very low. For example, any new objects that are launched by a new launch vehicle. So what launch vehicles do is they leave an orbit, they leave an object, and then they leave another object like a few hours from there or a few minutes from there. So these objects are essentially following each other. So you have a very low relative velocity between them. So in such cases, these simplifications don't work, and you have to use the more intensive 3D covariance. I will skip this equation, but that's how the probability of collision is essentially computed. It's a function of your state, which is represented by R, the vector R, and your covariance, which is represented by C star. So both of these things are important. So when I was talking about an unrealistic covariance, where you have a very small covariance, but your error is large in the state, it's going to affect your probability of collision. It's going to make the probability of collision unrealistic and an unreliable metric to work with because your covariance is it's just unrealistic. And now you were asking about the size of the object, right? So that's where this comes in. So HPR, or the hard body radius, is essentially dictating the size of the object. So when we are doing the integration of this probability density function, we do it over the size of the combined encounter, which is the hard body radius. And there are some other more intensive methods that you can use to calculate very realistic probability of collisions. One is the Monte Carlo simulation, where you're essentially sampling different states by looking at the covariances of these two objects. But again, these are some things that cannot be used in an operational process. They can be used in a more analysis sort of approach, where you're looking at previous encounters and seeing what the probability of collision was supposed to be. I already talked about the 2D method shortcomings because we have these stringent requirements that the relative velocity between two different objects has to be high relative velocity. If that assumption breaks, you essentially cannot use a 2D PC method. And rideshare missions, for example, are a really good example of where 2D PC methods cannot be used. There are some other methods that can be used in its place, like the 3D PC method. That's what we use at KHAN to calculate the probability of collision. And we have seen that time and again that 2D PC does not usually suffice when you're calculating the probability of collision of two different objects. This is a PC dilution curve. It essentially is showing you where your computed probability of collision is realistic and where it's not. So if you have a really, really large covariance on the object, for example, you're at LEO, let's say you have an object with 100 meters sigma uncertainty on your state versus 100 kilometers. So you have a very large covariance. You really essentially don't know where your object is because your uncertainty and envelopes are so high. So if you look at this curve, if you are going towards the right in the x-axis, your covariance is increasing in size. Essentially, in these regions, the probability of collision that you're computing is unreliable because your covariance is so large. So in these cases, what we tend to use is the maximum PC value. So we just calculate a one-sided conservative value of probability of collision, which is usually much higher than what it actually is, and gives that as a warning to operators. So this is the maximum PC because your covariance is so small, so large, and it could be actionable. And by actionable, I mean you might have to maneuver your satellite to get out of the conjunction. Okay, that's essentially covers the fundamentals of conjunction assessment that we do in operations. Atmospheric drag plays a huge role in our conjunction assessment. I didn't talk much about how we use it for collision avoidance, but we also do differential drag to get a satellite out of the way, especially when a satellite does not carry onboard propulsion systems. So you can use your cross-sectional area. If you can change your altitude, you can use a cross-sectional area to change your orbit and get out of the way of a conjunction. And that's also affected by atmospheric drag. But yeah, I hope you guys got something new from how we do operations and how atmospheric drag affects our operations.
Thank you. Okay, another question, Chad.
Yeah, your CDs are quite different from different objects you're tracking, is that correct?
Yeah, they are. Mhm.
So you basically, how many objects you have, and how many CDs to deal with, is that correct?
Yeah, exactly. So each object, sometimes these objects can be classified into a group. For example, if an operator is launching 10 satellites in a constellation, you will expect the CDs to be similar for all of them. So you can start with the baseline assumption of a same CD. But if there are different operators and you have different orbital regimes, plus you have different cross-sectional areas, the CDs can change a lot.
Another question is that you calculate your own TLEs, or you have to really just taking that TLE from some other places to calculate orbit?
Yeah, so sometimes we rely on TLEs just because, and those cases are essentially when you have an object that's just newly launched. You have data from nowhere. The only thing that you have is the TLE right after deployment. But we usually do our services with external data. So we have data providers. For example, some of the data providers that I was talking about, Leo Labs, RSky, all these data providers can provide data to different operators. And we have collaborations with certain data providers that give us optical data. And we use that to do orbit determination on the satellites.
You use AMSIS density models, or using other models?
We use MSIS, yes.
You use AMSIS?
Yeah.
You're not using the DOD?
We don't have access to the DoD one.
You don't have that?
Yeah. So only DoD can use the DoD model, unfortunately. Yeah.
Sarah, thank you.
Yeah, really interesting talk. So you were talking about the exponential increase of the satellites in orbit and these is going on. To what extent do you think the methodologies you're using now are going to be realistic to use in future? And how long do you think before there needs to be something completely different done just from the sheer number of satellites in orbit?
Yeah, that's a very good question, especially when it's coinciding with our solar max regime right now. Because so for collision avoidance and conjunction assessment, that's still not going to be a huge problem for companies like us, because we get the data from 18th, and that's their problem essentially to deal with. But when we do orbit determination and prediction for our customers, and as the number of objects are increasing in size, it has to be automated like very quickly, because orbit determination is still a pretty manual process. You do OD on a satellite, and from day to day, because the dynamics can change, the measurement quality can change, and you have these effects of space weather storms, the human in the loop has to go and look at the solution and tune parameters and make the solution converge. So those things need to change very soon. I can't give you the time, but maybe like in the next few years, probably. And we just know from hearsay that even the 18th has limited number of people that can go actually do these things, right? Like the number of orbit analysts that actually do these processes are limited. Like the number of humans employed are limited. And as you have these launches, which are launching hundreds of satellites in a single launch, like hundreds of objects in one single launch, the cataloging process takes too long. So automation there is also going to be very important. And that needs to happen now. Like that's something that needs to happen now.
Thank you.
So you said that like you are the commercial operator, one of the commercial operator. You don't have access to the HASDM results.
Yeah.
But what about the other way? Does HASDM have access of your data? So
Yeah.
all of this so that it can make the HASDM more and more accurate.
Yeah. So
Okay.
HASDM essentially relies on So the US Air Force is tracking all these objects, right, through the space surveillance network. They have all that data. HASDEM uses a subset of these objects, I think 80 to 90 calibrated satellites. So objects with very stable cross-sectional areas where you know that the CD is not going to change much. So the scale factor really provides you information on the atmospheric drag. So they have their own information, but they also ingest owner-operator ephemerides. So anything that we do orbital elimination on, we are providing to them. Anything that other operators are doing orbital elimination, their own assets, they're providing to them. So they have all this information. We just don't know how they're using it because it's a black box. Like we don't know what objects they're going to be using in the future. But I think it would make sense for them to use objects that are well tracked by commercial operators that are
Because the HASDEM is essentially data assimilation.
Yeah,
It
exactly.
used to use like 80, 90 objects.
Yeah.
That's not a very big number.
Yeah, it's not.
And like a space, even Starlink satellites, there's so many now,
Yeah,
like several thousand now.
yeah.
And if it can incorporate those data,
That would be amazing. Yeah. Yeah.
Yeah, so if it has used a lot of data, it can make it really accurate.
Yeah. And I'm pretty sure they're going to do that. It's just that we don't know when and how.
If they are using it.
Yeah.
And also you showed us slides that is that last year that conjunction, the number of conjunctions showed a number of conjunctions,
Mhm.
a lot of conjunction.
Yeah.
That means the collision happened.
No, that means that they got very close to each
Oh,
other.
okay.
So the
All right.
operators had to like move their satellites away.
All right. Yeah, because if you for collision avoidance, it's only for the satellite operator they can do the avoidance.
Yeah. Yeah.
But for the like space debris and other not operating satellites,
Nothing can be done.
nothing can be done. They
Nothing can be
just
done.
happen and
Yeah.
make more
Yeah.
space debris.
Yeah.
Yes.
Yeah, that's the worst part. So that's where like debris mitigation strategies come into play. Like some companies like Astroscale, they actually had a demonstration mission last year where they demonstrated that they could capture something. But we are very far from like actually having a large scale cleanup of space. But if a debris collides with another debris, nothing can be done. It's just going to happen. Yeah.
Question. So maybe I'm not sure if I understand it correctly. You said the number of debris never really decrease. It just keep increasing.
The number of net objects. So in the number of debris do decrease because they essentially decay into orbit, especially in low Earth orbit.
Mhm.
But the number of objects that we are adding into space, it's always going to be higher
Yeah.
than
So there's a net increase,
the net increase.
like a big
Yeah.
increase of the space debris.
Yeah.
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 So they would deorbit, for example, like think after the major storms, that would.
Yeah. Especially after a major storm, you see a lot of decay.
Okay.
The rate of decay increases by a lot.
Finally,
Yeah, sure.
what's your definition of LEO? Exactly.
That's a good question. In terms of just atmospheric drag effects, I would say what matters to us is under 1,000 kilometers because that's where atmospheric drag really plays a role. But LEO by definition is, I think, 5,000 to 6,000 kilometers. But anything above 1,000 kilometers, drag doesn't really matter as much.
Okay.
Do people online have any questions? I see no. Let's thank the speaker again.
Yeah.
Everyone will come